Hi, welcome to lesson 8.1. For today's lesson, you are going to need the following materials. You're going to need a full sheet of graph paper cut in half. Instead of a scratch paper, you need to use a half sheet of paper for a graph. So I want you to go ahead and make sure that you paste that on page 221. So it's supposed to look something like this. It goes right through most of it, just like that. Now, on the next page, we are actually going to blend in the activity for the first and the second page right in this graph right here. So you guys can cross off the second page because we're going to do the activity on the graph paper. Now, on page 223, we are going to put problem number 1 right there. Okay. We are going to put problem number 2 right here and problem number 3 right here. Turn the page over and we are going to do problem number 4 here, problem number 5, and problem number 6 down here. We're going to go over these in just a bit. Okay, so let's go ahead and get started on page 221. Okay, so I did modify the original activity just because I think the activity that I have in mind is a lot more simple and easier to understand. Okay, so what we're going to do here is we are going to draw 2 right triangles. One of them is going to be the dilation of the other with a scale factor of 3. So the first one that I'm going to draw is going to be triangle ABC, and I'm going to use a special right triangle that measures 3, 4, and 5. Okay, so this is my 3, this is my 4, and I know this length right here is going to be 5 because it's a very important Pythagorean triple. Okay, so the length of this triangle right here is going to be 3, 4, and 5. Zoom in a little bit. Okay, so 3, 4, and 5. Now I'm going to call this triangle triangle A, B, and C. Now I'm going to dilate this and I'm going to use a scale factor of 3. That means that I want a right triangle that is going to have the same measurements but multiplied by 3, meaning a 9 by 12 and then hypotenuse of 15. So right here, hopefully I have enough space. I'm going to have 3, 6, 9, and then 12 this way. 2, 4, 6, 8, 10, 12. Okay, so this length right here is 9. This length right here is 12. And it is, of course, a right triangle. Now, I could do this with any type of triangle, but because I am going to be dealing with an area, I wanted a shape that is going to allow me to find the area very easily. So I know that this length right here is going to be 15. Okay, so I'm going to call this triangle, I don't know, let's call it D, E, and F. Now, one of the things that we have talked in the past is about corresponding sides. DE corresponds to AB, DF corresponds to AC, and EF corresponds to BC. If I ever wanted to find out a scale factor, say I didn't know that and I was given these two, what I would need to do is set up a scale factor ratio, and I can find it. I can do DE to AB, DF to AC, and EF to BC. So one of the things that I want to talk about here is the fact that this is the scale factor for the length of the sides. Okay, so and I can verify this, like this. I can do 9 over 3. I can do 15 over 5, and I can do 12 over 4. And you notice that you can reduce these, and you're going to get 3, which is the scale factor of the sides. But what about the perimeter? What about the perimeter? So if I look at the perimeter of triangle ABC, and then look at the perimeter of the other triangle, what are we going to notice? Okay, triangle DEF. Okay, so the perimeter of triangle ABC is very simple. All you have to do is add your side lengths. That's going to give you 12. Add the side lengths of this one. 9 plus 12 plus 15. You add those all together and you get 46. So how does the perimeter of DEF compare to the perimeter of ABC? Now over here, when we were looking for the scale factor of the sides, we did the side from here to here. Okay, so basically from the image to the pre-image. We're going to do the same thing here. So I'm going to find the ratio of the perimeter. I'm going to just call it PER for that triangle. Perimeter of triangle DEF. And I'm going to compare that to the perimeter of triangle ABC. Now, we already know what this is. This is going to be 46 divided by 12, which happens to be, guess what? 3. So, look, it's the same as the scale factor of the sides. Okay? So what can we get through here? We can get here that the scale factor of the sides, okay, is the same as the scale factor, okay, of the perimeter. They're the same. So if you know the scale factor of the sides, you know the scale factor of the perimeters. Now, here comes the tricky part. What about the area? Hopefully I will have enough space here. If not, I might have to add a little space to the back here. So what about the area? Okay, so let's look at the area of the original triangle. This one right here, because it's a right triangle, I can easily find the area of ABC, of triangle ABC, by simply doing 3 times 4 divided by 2. Okay, so 3 times 4 is 12 divided by 2, that is 6. Well, what about the area of DEF? The area of DEF is going to be 9 times 12, divide that by 2. So 9 times 12 divided by 2, okay? So then that's going to give me 54. So if I were to do, again, the ratio of the areas of DEF to ABC, I would get the following. 54 over 6, and that is going to equal 9. Notice that that is not the 3 that we originally got. However, check this out. Isn't that the same thing as 3 square? It sure is. So how do these compare? Okay, so you have the scale factor of the sides be the same as the scale factor of the perimeter. For the scale factor of the area, it's equal to the scale factor of the perimeter and the side length quantity square. So if you know the scale factor of the side length, all you got to do is square it to get the scale factor of the area. And we're going to use this concept heavily in some of the problems that we're going to see. Okay? All right, so let's go ahead and move on to the examples. We have 6 of them. So turn to page 223. But before we do that, let's go over a few things on 223. Okay? So in the diagram below, triangle ABC is similar to triangle DEF, and you can write it. ABC is similar to DEF just like this. Just like we had a symbol for a congruent statement, we have a symbol for similarity, which is a little squiggly line. It's kind of like a congruent sign without the equal sign. So a similarity transformation preserves angles, and we already knew this from chapter 4. So corresponding angles are going to be congruent. Similarity transformations also enlarges or reduces a side length by a scale factor of k. How do we find this k? Simply divide this by this and you get your scale factor. All right, so we've talked about corresponding angles. In this diagram, C corresponds with F, B with E, and A with D. Their ratios would be DE to AB, DF to AC, and EF to BC. And they all have the same scale factor K. So we can do the same thing with the perimeters, which brings us to our next page. Now, corresponding lengths. If two polygons are similar, then the ratio of any two corresponding side lengths in the polygon is equal to the scale factor of the similar polygon. So this is what we're going to use on example number 1. What this is basically saying is that if you have two polygons, not necessarily triangles, two polygons that have similarity, that they tell you that they're similar, that means that the ratio from one to the other should be the same for all the corresponding sides and lengths. Now, here comes the part that it seems like it's very difficult, but honestly, it's really not. If two polygons are similar, then the ratio of their perimeters is equal to the ratios of their corresponding side lengths. So pretty much what we just did, PS divided by QN is the same as QR divided by LM, as QP and LK, and RS to MN. They're all going to be reduced and pretty much give you the same thing. Now, for the area of similar polygons, if two polygons are similar, then the ratio of their areas is equal to the squares. That's the key word. Squares of the ratios of their corresponding side lengths. So notice that this is going to be the ratio of the areas. It's not necessarily going to tell you what the area of one polygon is, but you can use it to figure out what the potential area would be, which is what we're going to do in the following problems. So let's begin. Okay, let's take a look at the first example. Okay, in this first example, this is what we have. Let me zoom in a little bit. Okay, they tell you here that these two triangles are similar. That's what they tell you here. You can use this also to figure out what side corresponds to what side, just to see if there's any reflections or rotations that we're not aware of. So here you have RS and XYB similar, ST and YZ, and RT and XZ. So you can see that there is no funny rotations or reflections going on here. We can just directly, figure out what we got to do. So the first question for A, it says, find the scale factor for RST to XYZ. So here's the thing. When you're reading this, the second one is always going to be your image, which is the one that's going to go on top. Okay, so if they tell me that they're similar, you only really need to do one scale factor, not all necessarily three. You can if you want to. I'm going to do all three just because, but you only have to do one. So for example, what you have here is 18 to 30. So we have 18 to 30. I have 12 to 20 and 15 to 25. How do I know I have to put this one first? Because this one here is the second one. So now all I have to do is reduce it. These both reduce by 6, okay, to give me 3 over 5. This reduces by 2, actually by 4, to give me 3 over 5. This reduces by 5 to give me 3 over 5. You notice how all three of these are the same? That's why I say that you only need to do one of them. You don't need to do all three of them. You can if you want to. Now it says for B, list all the pairs of corresponding, list all the pairs of congruent angles. Well, those are the corresponding ones. So, for example, you have angle R, that's going to be congruent to angle X. Angle T is going to be congruent to angle Z. And angle S is going to be congruent to angle Y. Now, for the last part, it sounds like a very confusing question, but it really is not. It says, write a ratios of the corresponding side lengths in a statement of proportionality. So what we're going to do is we're going to write a statement of proportionality. So the way this is going to work is we're going to pretty much set up our ratios. Kind of similar to what we did here with the letters. So for example, XY corresponds to RS. Okay, ZY is going to correspond to TS. And XZ is going to correspond to RT. Now, if you put these in different order, meaning that this is over here and this one's over here or whatever, it's okay. There's no really set rule as to this one has to go first. Okay, so that, ladies and gentlemen, is example number 1. Let's look at example number 2. Okay, so for example number 2, it says in the diagram, DEF is similar to MPN. So they want me to find out what the value of X is. The value of X is in what is it called? The segment EF. EF corresponds to NP. So here's the thing. This is my image. Okay, so this right here, this is the side length that corresponds to that one. So which one am I going to put on top? I'm going to put this one right here because that's my image. MNP is my image. So the image one always goes on top. Always. All right, so I have 30 over X, and I'm going to set up a proportion equal to, now here's where I have two options. I can do 24 divided by 20, or I can do 18 and 15. I will get the same solution regardless of which one I do. Okay, so I'm going to do 18 to 15 just for the heck of it. Now, how do I know which one goes on top? Remember, the image always goes on top. How do you know which one's the image? The second one. Okay, so 18 over 15. Now you have two options. You can reduce first and then cross multiply, or simply multiply across, or do the cross multiplication. That's going to give you 18x equal to 30 times 15. Okay, so 18x is going to equal, let's see, I believe that's going to be 450. And then what you need to do is divide it by 18, and x is going to equal, I don't know what that is. Let me get my calculator. Okay, so 450 divided by 18 should give you 25. So the value of x is 25. So one of the things that you have to remember is to make sure you put things in order. The common mistake is that students will do 30 over x and then they'll put 15 over 18. It goes like this. 30 is to x as 18 is to 15 or 24 to 20. You have to do it in that order. A lot of people put 30 is to x and then they do 15 to 18. It's not a clockwise or counterclockwise. They have to follow the same direction. So that, ladies and gentlemen, is example number 2. Let's look at example number 3. Center that. Okay, in the following diagram, triangle UVW is going to be similar to QRS. So this one here happens to be the image. Okay, find the length of the median. Remember, the median is the segment that joins the midpoint. So here's the thing. Medians are also proportional to the median on this side. So this is going to be proportional to this. So we are looking for ST. ST corresponds to WZ. So I don't know what this is. I'm going to call it X. So remember, since this is the image, this X is going to go on top. So X is going to correspond to 12 because that's the median. Okay. Now, in this case, we're lucky that these lengths are the same length, so it doesn't really matter. So 36 is going to correspond to 16. So 36 to 16. Cross multiply, you get 16x equal to 12 times 36. Now I plug that in to the calculator and I get 432. And then you simply divide that by 16 and you get, I should show that, x is equal to 27. So that is going to be the value of this median. Okay, and that is example number 3. Now, for this example, I know with rectangles we can probably get away with doing the problem in a different way, but I want to apply what we already know about scale factors of sides and also how does that affect with the area. So one of the things that we need to remember is you have 3 scale factors. You have the scale factor of the sides, you have the scale factor of the perimeter, and you have the scale factor of the area. Okay, we're not going to do the scale factor of the area in this problem, so we're not going to worry about that. Remember that the scale factors for the perimeters and the areas are exactly the same. So looking at this problem, it says a town plans to build a new swimming pool. An Olympic pool is rectangular with length and width, so 50 by 25. The new pool will be similar in shape to an Olympic pool, but will have the length of 40. And they want me to find out what the perimeter of the new Olympic pool is going to be. So I'm going to have a new pool. Okay. Now here the length is 50, but the new pool is going to have a length of 40 meters. And what they want me to do is they want me to find out what is the perimeter going to be. Now here's the thing. The perimeter of this pool right here, if you notice that this is going to be 50 and that's going to be 25, that's going to add up to 150. So I'm going to use the fact that I already know what the perimeter of this pool is and use it to find this one. So remember, this is the image. Why? Because that came in second. So the perimeter of the new pool, I'm going to call it perimeter of the new pool. I don't know what that is, but I do know that the perimeter of the Olympic pool, okay, the old pool you would say, we already know what that is, okay? That's going to be 150. So we don't know what that perimeter is. I'm going to call that X. Now here's the thing. This scale factor should be the same as the scale factor for the lengths of the sides. So the length of the side here happens to be 40. And the length of the pre-image, the old pool, is 50. That's the part that's a little confusing. Okay, so I'm mixing in length with perimeter. Remember, 40 over 50 is going to give me the scale factor. That scale factor is going to be this one. But remember that the scale factor is the same for the scale factor of the perimeter, which happens to be whatever this right here would be. Because you get 150, actually you get whatever unknown here is, over 150. And all we have to do now is solve for x. Now, to make it easy, I could just divide by 10, make it easy. Okay, I get 5x equal to 4 times 150, which is going to be 600. Divided by 5, and x is going to be 120. That means that the perimeter of the new pool is going to be 120 meters. Okay, oh, can't see that. So 120 meters. And that, ladies and gentlemen, is example number 4. Let's look at example number 5 now. Now, this is the one that, remember we said about the different scale factors. We have the scale factor of the sides. We have the scale factor of the perimeters. And we have the scale factor of the area. Both of these have the same scale factor, but the scale factor of the area is the scale factor of the sides, quantity square. So in this diagram, DEF happens to be the image. It comes in second, so that's always going to go on top. So this one here is the image. So what I want to do is I want to find out what is the area of triangle DEF. That is my unknown. I don't know what that is. Okay, so let's set up the ratio anyways. The ratio of the area of the image to the pre-image should be x over 36. Okay, now on the side here, let's find out what the scale factor would be for the side, because what we just found out was this right here. This is technically the scale factor of the area. Okay, so let's find out what the scale factor of the sides is. So it's very simple, 5 to 10. So K is going to be 5 to 10, which reduces to 1/2. So now if K is 1/2, what is K squared? Well, that's going to be 1/2 quantity square. You square the top, you square the bottom, and you get K squared equals 1 over 4. So what are you going to do with that 1 over 4? You are going to set that one equal to this one. So x over 36 is going to equal to 1 over 4. And then all you got to do is solve the proportion. Cross multiply, you get 4x equal to 36. Divided by 4, and you get x is equal to 9. Which means that the area of this triangle right here is equal to 9 centimeters square. This is the kind of problems where you're going to be struggling quite a bit. It seems difficult, but it's really not. All you need to do is find the scale factor of the sides, which we did right here. Square it. You get the scale factor of the area. Set up your ratio for the scale factor of the area over here. And these two values are going to be the same. So you're going to equal this one to this one, like we did right there, and simply solve for x. And that's what's going to give you the area. Just remember that the second triangle, the second one that's mentioned in the similarity statement, is going to be the one that's going to go on top. Because remember when we did chapter 4 and we found scale factors, it's always the image over the pre-image. All right, let's take a look at the last one, number 6. Okay, so for this last one, it says decide whether these two are similar. So remember, we have to look at two things. We have to look at the ratio of the sides. So we have to compare two things. We have to find that the scale factor of the sides are all the same, okay? And also that the angles are the same. So if we focus on the sides, let's look at one thing. You have 8 to 12, because there's like this little mirror image right there. So 8 to 12, okay? Divide them by 4, and that's going to get you, actually, yes, yeah, divide by 4, that should give you 2 over 3, okay? That's this one to this one. Now, here you have 8 to 12. It's the same thing. 6 to 9. So 6 to 9 reduces by 3 to give you 2/3. So that one's good. Okay. 4 to 6. Okay. 4 to 6 reduces by 2 to give you 2/3. So that one's good. And 6 to 9, which we already know that is the same. So all the sides have a pair. Oh, can't see that. All the sides have the same scale factor, but are the angles the same? This one's the same. Are the rest of them the same? Well, let's see. So I grabbed a piece of patty paper, and I'm going to trace this. Okay, so I'm going to trace this one here, that one there, there, and there, okay? And I'm going to compare to see if these are true. So what I'm going to do is I'm going to flip it. I know it's kind of hard to see it on the video. I'm going to flip it because, you know, did a little reflection. This one's good. This one's good. That one right there, you notice that that is not the same thing, okay? So the angles themselves did not preserve. So you do not have corresponding congruent angles. So are they similar? No, not similar. And that was our last example. Thank you for joining us. Make sure you work on your extra practice.